Welcome back to Physics 152 Online. Having introduced Gauss's law in class, I'm now going to show a fairly detailed example of how to use it to calculate the electric field for a certain kind of highly symmetrical charge distribution. So first, here are the steps that we will always use when applying Gauss's law to calculate the electric field in the vicinity of some kind of charge distribution. It's only going to work when the symmetry of the charge distribution is fairly high. Although Gauss's law is always true, it's not always useful in allowing us to solve for the electric field. But when it's useful, it's extremely powerful. So first, given the charge distribution, we want to sketch the electric field lines for the charge distribution using the symmetry that's present. And so here's the example. We'll work it through step by step. Find the electric field a distance z above and below an infinite thin sheet with uniform charge per unit area sigma. So sigma is charge divided by area, and even though it says it's an infinite thin sheet, I'm just going to draw a small portion of that because I don't have a page big enough to make an infinite sheet. So the sheet is drawn. In this sketch, it's intended to be perpendicular to the plane that we're viewing, and so it's going into and out of the page. And we can tell just by thinking about the kind of force that a positive point charge would feel, we can figure out the direction of the electric field lines. Assuming that the charge that's on this sheet is positive, then the field lines will be pointing above and below that sheet away from the sheet. And so we know that much just by symmetry, and that's where we start in applying Gauss's law. Secondly, and this is the crucial step, we want to choose a Gaussian surface, which has to be a closed surface, that has one of its surfaces on the place where we want to find the electric field E. And this Gaussian surface should have an overall shape that makes the flux integral easy to evaluate. Usually this will mean having portions of this surface that are either parallel to or perpendicular to the electric field lines. Having then chosen a Gaussian surface, we want to sketch in the dA vectors that are normal to the surface, and there may be more than one because the surface may have different pieces to it. So, what's that going to be here? Well, we want to find the electric field at distance z above the plane, and so it would be nice if the surface that we choose has a flat part that's at that position, z above the plane, and then also below the plane. By symmetry, we can expect that for a certain distance z above the plane, the field there should have the same magnitude as the distance z below the plane. But we want our Gaussian surface to take advantage of that. So, a cylinder, using some dashed lines here to represent it, a cylinder that has, of course, a circular top and a circular bottom. If the top and the bottom are a distance z above the plane, then we can see that the intersection between the cylinder and this plane will be a circular cross-section. So we draw in this cylinder, and you'll notice once we draw in the dA vectors, there are three of them because there's a top surface and the dA vector pointing normal to the top surface. These dA vectors always point from inside to outside, so it points up. And then the bottom vector, the dA vector, points down. The dA vector on the side points to the right, and of course at different points on this curved surface it will point simply away from the center of the cylinder. So I'm just drawing one of the dA vectors here. You'll notice that all three of these dA vectors either are parallel to the electric field lines or are perpendicular to them. And it's this feature that will make the dot product inside the integral particularly easy to evaluate. So we are set up now in order to use Gauss's law in this form to evaluate both sides and then to solve for the electric field E. So those are the next three steps that we'll carry out on the next slide. We want to evaluate the dot product that's in that integrand, and sometimes we have to take that integrand and break it up into pieces. Notice that the integrand is for E dot dA, but the integral says it's for a closed surface. Well, this cylinder is a closed surface, but it's got three pieces. It's got a top, it's got a bottom, and it's got a side. So this integral will actually get broken up into three separate integrals in order to carry out the evaluation properly. So we'll evaluate the dot product in the integrand, simplify it using symmetry arguments. Then we'll evaluate the Q enclosed term on the right-hand side, and finally, if we're able to, if the charge distribution has a high enough symmetry, we'll be able to solve for the E that we want. So here's where we go. On the next slide, we're going to evaluate both sides and find E. So as I said, that flux integral on the left-hand side now gets broken up into three pieces. E dot dA integrated over the top surface, then the bottom surface, and then the curved or side surface equals Q enclosed over epsilon 0. Now right away we can say something about this E dot dA on the side because we notice that E and dA are perpendicular. And so that means it will go to 0, because the dot product of two perpendicular vectors is 0. So that's great. E is perpendicular to the normal vector, which is the direction of the dA vector. So that goes away and leaves us with just the first two. Now notice on the top and on the bottom surface, the E vector and the dA vector are parallel. And that means that the integral of the dot product will be E times dA times the cosine of 0, which is just 1. So both of those two integrals become E times dA for both the top and for the bottom. Notice now on the right-hand side, we've evaluated the enclosed charge, because since the Gaussian cylinder intersects the plane in a circle, we just need to find what's the charge that's on that circle. And the cylinder had a cross-sectional area A. Sigma is charge per unit area, and so sigma times A is the charge that's enclosed by that Gaussian cylinder. So we've taken care of the right-hand side. And now we're just a few short steps away from finishing the problem. The two E's here, one of them is for the top and one of them is for the bottom. And so we also can simplify this integral by realizing that when you're on that top surface or on the bottom surface, the electric field should be uniform. In other words, it should not vary to the left or to the right, because the plane is infinite. And so as long as you're the same distance above the plane, the value of E, the magnitude of E, should not change. So we can write this as, we can pull that E outside the integral because it's not changing across the top surface. We'll call this ET for top. We'll call the E in the second term EB for bottom. And so the very last step here is to realize that by the symmetry of the situation, as we mentioned before, the electric field a certain distance above the surface should equal the magnitude of the electric field that same distance below the surface. So ET and EB are the same. We'll just call them E. So that means that we have, when we evaluate the integral, we're integrating this surface area element, dA, added up over the top surface. Well, that's nothing more than the surface area of the top surface. And so that's simply A. So we have E top A plus E bottom A. And since the E top and the E bottom are the same, this becomes 2EA equals sigma A over epsilon 0. And that gives us, when we solve for E, the value sigma over 2 epsilon 0. We can check the units of this, and it turns out that it has the right dimensionality, because remember, electric fields will always have a Coulomb constant times a charge over a distance squared, and the Coulomb constant has the same units as 1 over epsilon 0. So the 1 over epsilon 0 is correct, and then having charge over distance squared, well, sigma has the right units for that because it's a charge per unit area, which is a charge over a distance squared. So the dimensions of this expression are correct. And notice, one really striking feature to this is that the magnitude of E doesn't even depend on the height z above the surface. So what we've learned from the use of Gauss's law, at least in the limit of a very, very large surface, an infinite surface, we find out that the electric field points away from the surface, above or below, and it has a magnitude sigma over 2 epsilon 0, no matter how close or how far from the surface we are. So this is a result that I certainly could not have guessed in advance without working through the mathematics of Gauss's law. We could have gotten a result like this using Coulomb's law, but it would have taken a lot more work because Coulomb's law is not set up to calculate the electric field for this kind of a charge distribution very easily. So I hope that you can understand the steps, and the reason that I go to the trouble to write out these reasons when I simplify Gauss's law through these various steps is I want you to make sure that you understand why we're able to do these things. And for homework assignments, I will expect you to not just show the mathematical work, working through steps, but also to supply the reasoning, to write down these short comments about what's true about the quantities E and dA that allows you to simplify it and move on all the way through to the solution of the electric field. We'll do more examples in class, but hopefully this gives you some idea of the power of Gauss's law and how we will use it to calculate electric fields. I'll see you in class.